Okay, so last week, the second half of the lecture, we did the concept of pullbacks. And the last thing, we looked at 4 different intuitions for pullbacks. They're an important category theoretic construction. And the last thing we had was the pullback lemma, which I have prepared in advance and restated on the board as stated last week. Only I've taken the liberty of labeling the diagram now, and that's going to be useful because we're going to start by proving the pullback lemma. I sort of set this as an exercise, but I want to do an example of a proof in detail, and this is a good example of a proof to do. But before doing that, I want to remind you of the definition of the concept of a pullback, and I know we did this last week, but I'm going to do it in a slightly different way. I mean, obviously it's the same definition, and emphasize slightly different things, which is going to, I'm going to present it as what the pullback is. As some of you may know, a pullback is a special case of a general construction in category theory called a limit. And I'm going to present the definition of a pullback in such a way that will lend itself easily to natural generalization here. So I'm not going to write words here, I'm just going to do it in pictures. So as you remember from last week, when we wanted, let's keep the notation the same. So what a pullback is, well, it's given, the given data that you start off with is a cospan, which we can draw like this, so a map F and a map G. And that's an example of what we call in category theory a diagram, so a collection of objects and a collection of maps. And a pullback is simply a limit for this diagram. Well, what does a limit mean? Well, a limit is a cone. So a cone is given by an object and a collection of maps, one into each of the objects of the pullback diagram. So each of the objects of the diagram for which you're finding a limit. In our case, this cospan. So the cone here is given by 3 maps, one from P to X, one from P to Y, which I'll call Q, and one from P to Z, which I'll call R. And the property of a cone is it's such a family of, it's an object together with a family of maps, one into each object in the diagram, such that every triangle commutes. So here we've got such that, so every triangle commutes, so the triangles are F composed with R, F composed with P is R. That's this triangle, and there's only one other triangle, G composed with Q is R. So such a data for a cone, it's given by 3 maps, but we see that the composite F with P and G with Q need to be the same. And given that they are the same, we don't really need to specify the map R because it is given by either of those 2 composites. So strictly speaking, a cone is 3 maps such that every triangle commutes. But in the case of this particular diagram that we're taking a cone for the pullback, we don't need to give this 3rd map R. It's enough to say it's given by 2 maps such that the square commutes, such that F composed with P equals G composed with Q, because that determines uniquely a cone because it determines the unique R. Okay, so a pullback is such a cone that has the property that for any other cone, so another cone is going to be some other W, another collection of 3 maps, an X, a Y, and a Z. But once again, it's a cone for the same shape of, well, in fact, for the same cospan that we started with. So once again, we only need to give the 2 maps. So I'm going to call them X and Y here. So for any W such that, and those two maps X and Y such that now F composed with X equals G composed with Y. And then the property is, so it's a cone such that for any other cone, or for any cone, there exists a unique map from W to P that is a map of cones. And a map of cones means, once again, all the relevant, well, all the triangles that make sense commute. So here there exists a unique, I think I called it W last week, so maybe I didn't, but anyway, let's call it W. So there exists a unique map W such that now the relevant, well, all the triangles that make sense commute. And there are two triangles here, a triangle from, so we're asking for P composed with W is X and Q composed with W equals Y. So using this kind of color coding, we have a pullback of the black stuff is a cone, which is this particular cone. So that's a span. The black stuff is a co-span, such that for any cone, that's another span, there exists a unique map of cones a unique W, which is a map from the green cone to the blue cone. Okay. This pattern, we start off with a diagram, which won't always have this shape, but for other kinds of limits, it's going to have a different shape. For any diagram, a limit is a cone such that for any cone, there exists a unique map of cones into the limit cone. So that's going to be the general pattern of a limit, and a pullback is a special case. So anyway, that's refreshing your memory what the pullback is with a slightly different perspective. I now want to give you one example of some category theoretic reasoning carried out in detail, proofs using diagrammatic definitions. I'm going to prove one of the statements of the pullback lemma, namely statement 2. I'm actually going to prove a slight generalization, because that's the statement that the proof naturally accommodates. So 2 generalized, which is if AB is a pullback, and instead of assuming that B is a pullback, we remember from last week we had the concept of a pair of maps in a span being jointly monomorphic. Namely, we can use them to test the equality of maps into X we need to use composition with both the maps H and F prime to do that. I'll remind you of the definition when we come to the point in the proof. And we had the little proposition, which is very easy to prove, that any pullbacks in any pullback square, the span that is the pullback is a jointly monomorphic pair. And actually all we need for this property to go through is that if AB is a pullback square, so this outer square is a pullback square, and the property that automatically holds if B is a pullback square, which is that the pair of maps H and F prime are jointly monomorphic, so an H prime and F are, I'll just write jointly mono, people sometimes say jointly monic, then A is a pullback. Okay. So I'm going to prove a generalized statement. Okay, so let's clear the board here.
Professor,
Yes.
It's impossible that there are F prime and H jointly mono, not H prime and F.
It's not just possible, it's yeah. Sorry, so that's so indeed. This we want something weaker than assuming that B is a pullback square. If B is a pullback square, it's H and F prime, these two maps that are jointly mono. So thank you for spotting that. I think we would have come to it at some point in the proof. It's important to have it stated right. Right, so we want to prove, so proof of two generalized. So we assume AB is a pullback. And let's get it right. H and F prime together are jointly mono, jointly monic, jointly monomorphic. And we want to show that A is a pullback, the square on the left. Want to show A is a pullback. So I'm writing all that statement up here so that I can erase the top part of the board. And what I'm going to do, I want to show you how one does this kind of reasoning in category theory. It's kind of follow your nose, but it gets a little bit technical nonetheless. So there's nothing really difficult. There aren't any deep insights to have, but nonetheless, you have to just be, there's so much notation around, you have to be a little bit careful. As I wasn't when I stated the generalized property at first. So that A is pullback, so we need to show that for any cone for this span here, this co-span here, on the A square, there's a unique morphism of cones from that cone into the cone from H prime and F double prime. So let's do the logic on the left and the picture on the right. So suppose, so a cone is going to be, well, a cone is going to be given by an object. What do I use? I do use W. It's going to be given by an object W, a map here, which I'll call X prime from W to X prime. And the map here, which I call Y double prime, from W to the object Y double prime, with the property that F prime composed with X prime is equal to G prime composed with Y double prime. So suppose we have X prime and Y double prime is two maps such that cone property holds, so that the square we've made commutes. So F prime composed with X prime equals G prime composed with Y prime. Well, let's just state immediately what we want to show. We want to show that there's a unique map from this cone, a unique map of cones from this cone to the cone that we're trying to show is a pullback. So in other words, we want to show there's a unique map, which I think I call little w. Yep. So we want to show is a unique map W, little w, from the object W to the vertex here of the A square to X prime that has the properties that it's a map of cones, so namely the two triangles commute, so such that H prime composed with W equals X prime, and so that's, so we want the map to fit in here, so that's the one triangle here, and the other one is F double prime composed with W, F double prime composed with W equals Y double prime. I'm not writing W in the diagram because we don't have it yet. I want to have the diagram record the data we have, and I want it to be formed in such a way that we can use it, which is that whenever we have two paths, so everything in the diagram commutes. So whenever we have two paths between the same two objects in the diagram, they're equal. So I'm being careful to write it in this way. And before we go on, I want to note that if we have such a W, it also has an additional property. So note, any such W also satisfies a further equation, which is going to be useful later. So it also satisfies trivially the equation that if we compose H with H prime and W, so W is here, then we've got H prime, and we can further compose it with H. And I'm going to stop, for convenience, I'm going to stop writing the composition circles. I'm just simply going to write H prime W, meaning the composition of the three. Then that, of course, equals H of X prime. That's just trivial. These two maps are the same, then if we pre-compose them both by H, they're still the same. But it's an important little observation, this, for the proof. Now, we're going to use now the property that AB is a pullback. Now, to use that property, we need a cone for AB, but we have such a cone because we'll consider here just the map from W to X that we already have, namely H composed with X prime. Let's check that the square commutes. So we can indeed use the pullback property of AB. So note that. So I want to show that F composed with this map is the same as G composed with G prime composed with Y double prime. But F composed with this map is so F composed with H, F composed with H composed with what's it called? X prime. But F composed with H composed with X prime, well, because the B square commutes, that's the same as G composed with F prime composed with X prime. And that's the same as G composed with, what was it called? F prime composed with X prime. But F prime composed with X prime is the same as G prime composed with Y prime. So this is the same as G composed with G prime composed with Y prime. And that's exactly what we wanted to show that these two outer maps are a cone for the diagram, which is the bottom right cospan of the AB rectangle. Okay. It is, thank you. So since AB is a pullback, there exists a unique map from little w from W to X double prime such that, well, it's a map of cones between the H composed with X prime and Y double prime cone to the H composed with H prime and F double prime cone. So in other words, H composed with H prime composed with W equals H composed with X prime, but H composed with H prime composed with W equals H composed with X prime, and G composed with, and f prime composed with w equals y double prime. F prime composed with w equals y double prime. So one might be tempted to write this w in here, but I'm not going to do so. Can anyone see the reason why not?
Those triangles don't.
Well, we haven't yet shown that this triangle commutes. So we've got that W makes this outer triangle. So W composed with H and H prime together is equal to this outer leg. But that doesn't yet mean that this commutes. So it'd be misleading. I want the diagram to always, I want to be able to use the diagram. So I only want to put maps in the diagram if everything clearly commutes. And actually the whole point is we have a unique W that makes these two equations true. This one we wanted, and we wanted a unique W that makes this one true and another equation true instead. That equation implies the one we've got, but not vice versa. But by this observation that we've noted, it's sufficient now. All we need to do is show that this unique W also satisfies this equation. So then,
That's the question. That last equation, is that F double prime or F prime?
sorry?
And the last equation, that's
Yeah.
prime double, is that F double prime?
It is. Oh dear, these should be in black. These darn primes. Darn is the kind of word that people used to say a long time ago when damn was a swear word, but by current standards, damn is very mild. I mean, you turn the radio on nowadays, and so I remember when people went ballistic in the 1970s when somebody said shit on British television. Now, anyway, so this is nothing to do with category theory, but anyway, by what we noted above, we just need to show, in order to show there's a unique W that satisfies the two properties we want, we just need to show that the W we've got actually satisfies the property that we don't know it satisfies. So by what we noted, it is enough to show that the W we have satisfies H prime composed with W equals X prime. We've got two maps into X prime. We want to show they're the same. And this is where we're going to use the joint monicity of H and F prime. So that means to show this, it's enough to show that both these maps composed with H are the same, and both these maps composed with F prime are the same. This holds by the joint monicity of, what was it, F prime and H, because on the one hand, if we compose both these maps with H, they are indeed equal. H prime H composed with H prime W is H prime W. That's the same as HX. So HX prime. We already have that. And the more interesting one is if we compose F prime with each of these maps. Well, let's start with F prime of H prime of W. Well, F prime of H prime of W have we got something with that somewhere? Let me check my notes. Well, this is, let's see why in a moment. This is G prime of F double prime of W. Okay, yes, F prime, H prime composed with W, that's the map here. Well, we can use this square. So that's the same as G prime composed with F double prime composed with W. That's using that square. And this, well, F double prime of W is, sorry, that's a Y, isn't it? A Y double prime, is it? Yes. So this is G prime of Y double prime. And G prime of Y double prime, because we had a square, because we started off with a cone for this pullback square with F prime and G prime. So G prime of Y double prime, that's the same as F prime composed with X prime. And that's what we wanted. If we put F prime in front of both of these maps, then we get the same thing. And we're done. So that's it. If we pre-compose both of these with F prime and H, they're both equal. So the property of joint monotonicity says in that case, these two maps are equal. So we're done by joint monotonicity. Whoops. Okay, good. Right, so those are pullbacks. And now let's move to another kind of limit. So what I want to do today is introduce limits in general, and we're going to see several other examples of limits and then general results about limits. So limits are very fundamental construction in categories. So like pullbacks, it's a construction we perform inside a category itself. It's a structure we find inside a category. So the next thing I want to do are binary products. Now, our diagram is going to look like just a pair of objects, but no arrows at all. So what is a cone for this diagram? I can't remember what my color coding was, but anyway, so now my diagram is blue. So in this case, a cone is going to again be given by an object and a map from that object into all the objects in the diagram, such that all the triangles commute, but there aren't any triangles because we don't have any maps in the diagram. So in this case, a cone is simply a pair of maps. And we want, again, this to be universal with respect to any other cone. So namely, if we have any object Z and a cone, let's call it little x and little y, and a cone to the diagram. So that's again just a pair of maps. There needs to exist a unique let's call it Z. It's a map of cones, so namely all the triangles that formed by Z between the two cones commute. So to put that in words, let's forget the color coding for the, just so I don't need to change pen too often, but a binary product for objects X and Y is a pair of maps. Well, it's an object P. Well, let's just say, well, it's a span because it's an object P together with a pair of maps. It'll be to X, Q to Y, such that for any other span between X and Y, or any span, so little x with some domain Z, little y to the object Y. There exists a unique unique map little z from z to w, which is a map of cones, which means the two triangles, all the triangles, which there are just two here, so such that the two triangles, so this triangle, sorry, this one, that's P composed with Z equals X, and Q composed with Z equals Y. And we say, just like we say, a category has pullbacks if for any co-span there exists a pullback span. We say the category has a binary product if for any pair of objects there exists such a product span. So C has binary products if for any pair XY in the objects of C, there exists a product span as above. Now, I'm not going to write down the details because we're going to go more general, but hopefully it's not going to surprise you that in the category of sets, products exist, and the product of X and Y is simply the Cartesian product of the two sets X and Y. So P here would be the product X times Y, the product set X times Y. Little p is the first projection, and little q is the second projection. And that enjoys this property as it's easy to see. We're going to write something more general later, so I'm not going to put that down now. But we often use that notation also in categories. So, if products exists, we often write we often have a chosen product in mind. So a product is just any span that satisfies this property, but we often have a specifically constructed span in mind in the categories we're working with, and we tend to write X times Y for that chosen object and the chosen span, and we write little pi 1 and little pi 2 for these projection maps, which are part of the span, or a chosen product. You can see, so we often use just the usual Cartesian product notation, and we often, instead of, sorry, this, I don't know what this W is doing here. So there's this weird thing when you're dealing with variables in English that your typical variable is X, and when you want the next variable, it's Y, and then the next one is Z, or if you're American, it's Z, and after that, for some reason, you go back to W. I mean, maybe in Slovenian, you just go to J, and it would be easier, because you have an actual. So then, do you use J for a variable? No, well, you should do. More logical than W. Anyway, this should have been P, and we often write, instead of little z here, we often write this as just a pairing notation, the two maps, little x and y. So we're pairing the two maps, little x and y, together to get a single map into the product. Okay, that's a binary product. The reason I didn't want to go into the example in detail is because that's a special case of something more general. Well, in category theory, everything is always a special case of something more general. And somehow part of the trick of doing sensible things is to find the right level of generality. So some people used to think category theory is just too much generality, and that it's so general, it's too general. But it's now really so core to so many areas of mathematics that people have realized it's really useful, but you know, you still have to find somehow the right level of generality. Anyway, binary products, because they're called binary, they're almost self-evidently a special case of something more general, and one natural level of generality is general products, or products of where instead of two objects in the diagram, you have some collection of objects in the diagram. Could be some finite collection of objects in the diagram, or it could even be an infinite collection of objects in the diagram. So the natural way to do that is to index the object of the diagram by an indexing set I. So we're going to look at I index products in general category C. So I here is a set. So in this case, we want to look at what a product of a family X sub I, so little I, the index I of objects of C is. So we think of this as a diagram. Every element of the index set I is giving us an object of the diagram. There are again no maps between the objects. It's just a diagram consisting only of objects. So product is again a cone. So what's a cone now? Well, it's again an object P and a map from that object into every object in this family. So it is an object P and a family of maps, which I'll call them little p sub I. So one for every object in the family, a map from P into that object. Again, so it's a cone. Again, satisfying the same universal property as it's called, that for any cone, there is a unique morphism of cones from that other cone into this product cone. So such that, so for any other object Z, could be the same object, doesn't matter, and family, so a cone from Z, which I will call these maps little x sub I into the objects x sub I. There exists a unique map of cones from Z to P. A unique map, which I'll again call little z, from Z to P, such that all the triangles commute. Well, maybe it helps to have a picture. So we've got our objects x sub I, one for each index I in the diagram. For every P, we've got a map little p sub I. Sorry, not for every P. For every x sub I, we've got a map little p sub I, which is in the limit cone, the product cone. We've got the other cone, which is an object Z together with maps little z sub I. And we want the triangle formed by the map little z. Sorry, this I was calling little x sub I. We want all the triangles formed. So there's one such triangle for every index element little I in the index set I. So we want all these triangles to commute. So such that for all index elements I, p sub I composed with little z equals x sub I. Okay. So I'm going to talk about examples, maybe after the break. before doing so, let me say how this generalizes the binary case. Well, that's obvious. In the case that this is a two-element set, what this gives us is exactly the definition we had of a binary product. So this is now a generalization for any family of objects. So binary is a very natural restriction of this. Finite product is also a natural restriction of this, but so finite product is when I is a finite index set. Another very important special case, which looks like it's going to be trivial, is the case in which the index set is empty. So a special case, I equals the empty set. Maybe I need to move the camera. So what is an empty product? Well, so an empty product, we're asking for the product of an empty family of objects of C. Well, there is only one empty family. There is an empty family, but there's only one of them. So there is one empty family of objects. So a product for it is going to be an object P and a cone. So a cone is going to be an empty family of maps. Well, there's always an empty family of maps. There's exactly one empty family of maps. So a cone is just simply an object. In this case, the product is simply an object, which I'm going to call T, because a cone is just an object. Because the empty family of maps, there's always an empty family of maps, it doesn't do anything. So such that for any other cone, that's for any other object, there exists a unique morphism of cones. So that's just, there exists a unique map from any other object to the object we have. So it's simply an object T such that for any object Z, there exists a unique map from Z to T. There's only one map for any object Z. There's only one map into T. And this is a very important special case of a product, and it's got its own name. So such an empty product, or such a T, is called a terminal object in a category. An object with the property that from any other object, there is only one map to that object T. And the usual notation is 1 for the terminal object, and the unique map is written with an exclamation mark. Sometimes you put sub Z to make it clear what the domain of the map is for the unique map. So we've now seen a few examples of what are called limits in a category. Pullbacks, binary products, I-index products, and a special case of those, terminal objects. In each case, well, I haven't emphasized it today, but I did mention it last week for pullbacks. The structure that you define, the limit cone, so the pullback cone, the product cone, the terminal object, is unique up to isomorphism. You might find many different representatives for it in a category, but only two of them will be isomorphic to each other. I said last week, it's a good exercise to try and convince yourself of this, not to prove this in the case of pullbacks. I'm going to actually prove it in the case of the terminal object, which is the easiest case. So I want to show that any two terminal objects are isomorphic. This is really simple. So suppose T is a terminal object. Then there's a unique map into it from any object. So there's a unique map into it from itself. So the only map from T to itself is the identity. So let's just write it like this. 1T, the identity on T, is the only map from T to itself. And suppose T prime is another terminal object by the same argument. 1T prime is the only map from T prime to itself. So given two terminal objects, we have the unique map from T to T prime. The unique map from T to T prime, and the unique map, which I'll call U prime. So this is because T prime is terminal, and this is because T is terminal, the unique map back. And then, sorry, this should be U prime. And then U prime composed with U is, of course, a map from T to T. And since the identity is the unique one, that's the only one. So that's the identity on T. And U composed with U prime is a map from T prime to T prime. And because the identity is the only one, that of course equals the identity, because the identities are the unique maps. So it's a very, very simple argument, but actually this argument for terminal objects, if from the right perspective, which we won't come to today, but from the right perspective, this is actually the reason that arbitrary limits are isomorphic to each other, because they're all defined as terminal objects in a suitable category, and they're isomorphic because terminal objects are isomorphic. But in any case, for any of the examples we've considered so far, if you prove that, say, two products of the same diagram are isomorphic, you basically use the same argument here. There's a unique map of cones, and the identity is a map of cones, and therefore the maps between two different product diagrams, you compose them either way, they give you the unique cone morphisms from the diagram to itself, and those are necessarily the identities. Right, okay, I've overrun by 5 minutes, but let's start again at 1:15, if that's okay, and rather start earlier and end earlier. Okay, so we've seen the general notion of product. I didn't give examples, but that's because they're almost sort of obvious. So hopefully you have examples in your mind already. But let's, for the sake of it, list examples. I won't write this on the board, but just like with pullbacks and binary products, we say a category has products if for every indexed family of objects, that indexed family has a product cone. Or we say it has finite products if for every finite index family, that finite family has a product cone. So unsurprisingly, perhaps, set has products, and the product.
Oh, you need to change the camera.
Thank you. I had the whole break to set things up and I failed to do so. Anyway, the product of a family of sets is, of course, just the Cartesian product of the sets as usually defined. And the cone is with the maps mapping a family to its projection on I. So those are the projection maps from the product to the xi. So it's exactly what you would expect. It's not exciting. The only thing is the notion of category theoretic product determines this structure up to isomorphism in the category of set, namely up to bijection. The category of vector spaces over a field K, again, has products. And the product in this case is again just the Cartesian product, the I-index Cartesian product of vector spaces. Group has products. The product in this case, a product of a family of groups, is what's called the direct product of the group, of that family of groups. So here we have the Cartesian product, direct product. I think people sometimes talk about direct product of vector spaces as well, especially if you view vector spaces as modules, then people often talk about direct products as modules of modules. A direct product of groups. The category of topological spaces also has products. And unsurprisingly, the product of a family of topological spaces is what's called the topological product of the family of spaces. So it's the topological product. So it's kind of, in one sense, obvious, but the interesting thing that's happening here is that because we're defining the structure using the category theoretic notion of limit, in all these example categories, the structure is determined up to isomorphism. So in the case of topological spaces, for example, the notion of product is determined up to isomorphism in the category of topological spaces, namely up to homeomorphism. So the notion of category theoretic product, this very general notion, but in terms of this universal property, forces upon us the product topology that comes with the product topological spaces. So when you do topology, I mean, I think in the case of topological spaces, that's the most complicated of these products to describe. When you do topology, the notion of product topology is from something. It's not very complicated, but it's something to get your head around. And here it's forced upon you because it is the unique topology that makes, up to homeomorphism, that makes the category theoretic product work in the category of topological spaces. So in the notes, I've included a proof of that. I'm not going to go through it in the lecture here, but it's also something to think about by yourself. And something else to think about is going to be the week 5 puzzle, which, having failed to get the puzzles actually into the lecture themselves over the last 2 weeks, I decided to bring this one in at an earlier stage in the lecture. So we haven't looked at the category of relations for a while. That was the subject of the first week puzzle. So the question is, what are products in the category rel of relations? They exist, but the point is to find a nice mathematical description of the products in the category rel of relations. Okay, I mean, I don't want to go on about products for too long. I just want to end with one little proposition, or don't remember if I call it proposition or theorem in the notes. Let's call it a proposition. So it's often important, does a category have products or not? And if it doesn't have general products, does it at least have finite products or not? So the category of finite sets, for example, of course, doesn't have general products, but it has finite products. Similarly with the category of finite dimensional vector spaces. So there's actually a very simple condition for a category to have finite products. So the following are equivalent. For a category C, I won't write for a category C. So firstly, C has finite products. And secondly, it's enough for C to have a terminal object by the way, it follows from this description of general product in set that the terminal object in set is any one element set. And those are the terminal objects in set. So for a category to have finite products, it's enough that it has a terminal object and binary products. And I'm not going to give you a proper proof of this. To actually write out a proof is a bit complicated. You can try to do it, and you'll see that there are lots of details to fill in, but the idea here is very simple. So, I mean, firstly, 1 implies 2 is trivial because the structure in 2 is special cases of finite products. They're products with finite index sets. So in the other direction, we want to show that, so I just want to show 2 implies 1. So in this case, the terminal object is the empty product. So 1 is, that's the terminal object, is the empty product. A product of a 1-element set is just the object of objects, is just the object itself. So the interesting case is for n greater than or equal to 2. So for n greater than or equal to 2, the product of n objects, x sub I from I is 1 to n, can be defined isomorphically just as an iterated binary product. So we take x1 times x2, binary product, bracket that, binary product that with x3, and so on, and just keep on repeating binary products until we get to times xn. Okay, so very simple idea. But the point is, if we want to verify we've got finite products, we can just use that condition. We've got terminal objects and binary products. Okay, so now we're going to turn to yet another form of limit. And once again, it's going to be a limit for a certain shape of diagram. And this diagram, so such a diagram consists of 2 objects, x and y, and a pair of maps between them. So a parallel pair of maps, f and g from x to y. So what's a limit to this going to be? Well, again, it's going to be a cone. So it's going to be given by some object E, say, and maps E, and let's go backwards down the alphabet, and D into x and y, such that f composed with E equals D to make the triangle, and G composed with E equals D. So once again, F composed with E is the same thing as G composed with E, and given that fact, we don't need D because it's determined by the others. So once again, the cone, just like with pullbacks here, the cone can actually be just expressed in terms of the map E, and we need F composed with E equals G composed with E. Such a thing, a limit cone, so a cone that is universal in the way I've described before with respect to other cones, is called an equalizer. So the formal definition is an equalizer of a parallel pair, F and G, Y in a category C, is a map, little e, from an object E into X, such that this equality holds, F composed with E equals G composed with E, and for any other cone, so for any map little z from an object, an arbitrary object Z to X, such that E composed with Z equals, sorry, F composed with Z equals G composed with Z. There exists a unique map of cones from Z to E. Unique map Z from Z to E. Such that it's a map of cones. So in that case, so we've got Z here, we've got little, am I getting my, oh no, are you, yes, are you, let's keep the notation consistent with what I was doing before. So let's call this one X. Doesn't really matter, of course, but so there's a unique Z in here. So such that E composed with Z equals X. Okay, so another notion of limit. And so we can get an understanding of what this means. Let's immediately look at, so again, sorry, equalizers are unique up to isomorphism. We say a category has equalizers if for every parallel pair such an equalizing cone exists, so such an equalizer map exists. And let's again look at them in the category set, because that'll give us some intuition for what's going on. So set as equalizers so given F and G, we define E is simply defined to be the subset of all those elements in X. Well, the point is we want to get a map into X that makes F and G equal when we compose here. So the obvious thing to do is to, well, this map as its image is going to have to land in the set of those elements here that are sent to the same thing by F and G. And the universal such map here is just going to be the subset of X that consists of all such elements. So we simply, the underlying set of E is simply the set of all elements of X such that F of X equals G of X. And E, the map E, is simply defined to be, well, the identity map, if you like, the inclusion map from this subset of X to itself. So it simply takes any element X to itself, so that goes from E to X. And it's easy to see that this, I mean, it's very easy to show that this satisfies the equalizer property. So equalizers, the way of thinking of them is as a category theoretic way of saying, give me back the subobject of X. Look at the weekly exercise for last week for the notion of subobject, and this is related to your homework. Give me back the intuitively give me back the subobject of X, which is the subobject on which the maps F and G coincide. Equalizers is kind of intuitively that construction in a category. And the idea of thinking of it as a subobject is justified by the following simple fact, which is an easy exercise. It's almost trivial to prove. So in any equalizer, or E little e to X, the map E is a monomorphism. So this is clear that the E we've defined this way, it's a subset inclusion, so it's clearly injective. But in any category, any equalizing map is a monomorphism. And it's a very important notion of monomorphism, this. So it's not true that every monomorph is not true in general in an arbitrary category that every monomorphism arises as an equalizer map. Those monomorphisms that do arise as equalizer maps have a special name because arising as an equalizer map turns out to be an important property. So a monomorphism that arises, that means that monomorphism, for that monomorphism, we can find a parallel pair such that that monomorphism satisfies the property of being an equalizer with respect to that parallel pair. So a monomorphism that arises as an equalizer, or can be displayed as an equalizer, would be another way of saying it, is called a regular monomorphism. And I just want to mention two facts about this. So in general, it's not true that every monomorphism is regular, but in the category of sets, it is true. So the first exercise is to prove that every monomorphism in set regular. Well, the proof that should be implicit because it's an exercise. I'm going to make that implicit now. The second exercise, so I said it's not true in general, in a category that every monomorphism is regular. In the category of topological spaces, it is not the case that every monomorphism is regular. The regular monomorphisms in the category of topological spaces have a very nice characterization. They're exactly the continuous maps that are what topologists call embeddings. So exercise 2 is to show that. So in the category top, regular monomorphisms are the coincide with subspace embeddings. Well, sorry, with embeddings. If you don't know what a topological embedding is, this isn't the place to learn topology. So in that case, ignore. I mean, you know, this course you do. If you know the maths of the related subjects, then you can do the exercise. If you don't, then that's fine. I mean, you can think about it if you like. There's a little trick needed for 2, and in the lecture notes that I'll put online, there's that trick is there as a hint. And it's useful to have that trick because you need to consider a topological, I mean, the easy way to prove 2 is to consider a topological space that if you're a topologist, you would never think of using, because it's a topological space with a really silly topology. Right. So, wrapping everything up, we've done. So we've looked at today and also last week. Let me get the camera in the right place. So we've got a list now of limits we've looked at. So we've looked at pullbacks. And these are limits for diagrams that had a particular shape. So let's put dots for the objects and arrows for the morphisms, but we won't give them names. We looked at products. So let's say binary products. These were limits for just when we have two objects. So high index products. Limits for a set of, so where we've got I, any objects, we think view it as a diagram of this shape. We've got the terminal object, and here we have the empty diagram. Equalizers. So, I mean, hopefully you can all see what we've done fits into this pattern. We started off with a diagram shape, and we considered the notion of limit for that diagram shape. Another one that I cover in the notes that I don't want to do in the lecture is what are called projective limits. And this is a limit for a diagram shape where you have a sequence, an infinite sequence of morphisms extending to the left. Okay, but I'm not going to do that in detail in the lecture. So what we've got in each case is diagram shapes are graphs. In the mathematical sense, the discrete math sense of the notion of graph, although in a certain sense, they're directed graphs because they've got the arrows have directions. And moreover, crucial for equalizers, we need to have the property that you can have more than one edge between the same two objects. So specifically, what are called directed multigraphs. Or sometimes digraphs or dimultigraphs or something. But anyway, let's forget about that. But anyway, however you shorten it, directed multigraphs is a bit of a mouthful. So I'm just going to call them graphs. So when I say graph, I mean a directed multigraph. So where the pictures are like this. There's another mathematical word for this. So AKA, also known as. So these are also called quivers. So I don't know if any of you have ever read Robin Hood in English, but a quiver is the pouch that an archer used to wear that they carry their arrows in. So that's a quiver, so it's something you carry your arrows in. So it's a nice poetical name for this, but it just seems very funny to me to, if you're doing mathematics, to start, and now we have a quiver and another quiver, and it doesn't kind of roll off the tongue for me. So I'm going to call these graphs, and I mean a directed multigraph. So what I want to end the lecture with is the general definition of limit for a diagram given by a graph. We've had these examples, the the last one, projective limit, is in the notes. So let's define a graph first. Now I mean, defining graphs, if you do discrete mathematics, it's like sort of lecture 1 of the course on discrete mathematics. Although we do need to be careful because we want, when we say graph, we mean quivers. But let's define it in such a way that it's kind of consistent with our definition of a category. So for us, a graph. So I'm going to use G for a graph. So now G up to this point in this course has typically been a group, but now it's a graph. And if anyone objects to the terminology graph, then you can think quiver any time I say graph, and you'll be fine. So a graph is given by a collection which I use the same notation as for a category, but we're not going to call these objects, we'll call these vertices.
Sorry, but the camera is out of focus.
Ah, right. Yes. There you go. Thank you. So a collection of vertices, and for any pair of vertices, a collection of edges directed from the first vertex to the second. And for every little uv vertices in G, a collection G sub uv of edges from U to V, or using graph theoretic terminology, with source U and target V. So I've written it this way because a graph is just the same data as for a category, except that we don't have identity. We're not requiring identity edges, and we're not requiring a composition operation on edges. And we have the notion of we say a graph is locally small, locally finite, using in the obvious way. I don't want to write the definitions down, but you know, it's the same as for categories. So locally small means every collection of edges is a set. Small means locally small, and the collection of vertices is also a set. Locally finite means every collection of edges is finite. Finite means locally finite, and there are only finitely many vertices. Right, good. We also need the notion of graph homomorphism, or let me just say graph morphism. So a graph morphism from G to G, let's say F from G to G prime, is given by a function F0 that maps vertices of G to vertices of G prime, and for every vertices, pair of vertices U and V in the objects of G, a function F1 for U and V from vertices from little u to V in G to vertices in G prime from F0 of U to F0 of V. So a graph morphism or a graph homomorphism is the expected thing given our definition of a graph. It's again, just like the graphs generalize categories, these generalize functors. It's the same data as for a functor, but we don't have identities in composition, so we don't require, it doesn't even make sense to require that identities in composition are preserved. And I think you can obviously see that such data here, these diagram shapes, so these are diagram shapes. I should have really called them shapes before. Can be easily written as graphs in that sense. Right. So here we have a category of graphs and graph morphisms. It's clear that any functor, any category is a graph, and any functor between categories is a graph morphism. So we have a forgetful functor from the category of categories. Well, we have to make a category, have the category of small categories. We have a forgetful functor from the category of small categories to the category of small graphs and graph morphisms. So let me write graph here, just to be equal to the, so that's, we define this the category of small graphs as objects and graph homomorphisms. I'll just write morphisms as morphisms. Right. Before carrying on, this is your hint for the weekly exercise 3 about understanding functor categories. So it's a delayed hint for weekly exercise 3. Okay, so we want to define what it means for a diagram given whose shape is a graph to have a limit. So a diagram over a graph G in a category C is simply a graph morphism from G to C. So C is a graph because it's a category. So we'll just write it D for the diagram from G to C. So when we started off with our diagrams in considering the different notions of limits, we were taking these graph shapes here. We were taking these graph shapes here, and we were assigning names to all the vertices as objects, and we were assigning names to all the arrows as morphisms. And such an assignment is given by a graph morphism from the graph, which is the shape, to the category. So given a diagram, a cone for the diagram.
The camera has lost focus again.
I'm not surprised. I'm struggling to maintain focus myself. Anyway, so a diagram, no, what did I want? Oh yeah, a cone for a diagram. Okay, well, let's think about what it should be. So for the diagram D. So a cone is going to be, so let's write the G in. So given my graph shape G into a category C. So a cone is going to be an object together with maps to all the objects in the diagram that we've got that we've got D. So it's going to be given by and now I do want to refer to my notes just to see what letters I use, which I've forgotten, even though I wrote it less than only a few hours ago. So cone for diagram D is given by an object Z together with a family R sub U of maps from Z to D sub U, U in vertices of G, such that, well, so the point is this is our vertex of the cone, and for each object in the diagram, so the objects in the diagram are the objects labeling the vertices in the graph shape. So the vertices in the graph shape are the U, the vertices U, and each one is labeled by an object given by the, so this is the D0 part, but just like functors, we're going to graph morphisms. I'll just apply them to vertices and apply them to edges. Okay, so for every vertex in the graph shape, this is the object we've labeled it with, and the cone is a family of maps, one from the vertex to each of those labeling objects, such that all the triangles commute. So the triangles are given by the edges. So here, so where Z is an object of C, such that, so all the triangles commute, so that means for any edge in the category, sorry, not in the category, for any edge in the graph shape, such that for every E, well, so we can say for every edge in the graph shape, so that's for every source and target vertex in the graph shape, and E, which is an edge from U to V. We want the diagram to commute, so the diagram is that, so we've got a map Z, we've got an RU which goes to DU, we've got a map RV which goes to DV, we've got an edge from U to V in vertices, that's E, and here we've got from the graph homomorphism an edge D sub E from between the labeling objects, so which is a morphism in the category. So we want that triangle to commute in C, that's a triangle in C, so DE composed with RU equals RV. Then a limit I want a different color. Limit for the diagram is a D cone, so it's a cone for D. Let's call it L for the limit map, and let's call these maps PU, like I was doing before. So PU is going now from L to the objects labeling the diagram. That is a morphism of cones, which mean that all the triangles, such that for any, that's not a morphism of cones, that is a cone, such that for any cone Z R RU as above, there exists a unique map little z from Z to L, such that all the triangles commute, so it's a morphism of cones, which means for all objects in the for all vertices in the diagram shape, rho u composed with z equals, sorry, not rho, that's p u equals r of u. So z, so for every d, so our cone is giving to every object in the diagram d sub u, so indexed by the vertices of the shape. Our limit cone gives the map p sub u. Our other cone gives the map r sub u, and we've asked for a unique map z here that makes all these triangles commute. Okay, so it looks very abstract, but it's basically exactly what we've seen in all the examples, just written in the general form of cones with respect to diagrams given as graph morphisms from a diagram shape. Right, so I do want to end by stating two really important theorems, and then we're going to go. So I'm going to very, very slightly overrun today, but maybe not. I mean, I do have to clear the board. If only these boards could clear themselves, it would be. So it looks like a very, very general notion, this notion of limit, and it is quite general, and that's what is one of the really powerful notions in category theory. But we've actually done most of the work we need to understand it. So I'm going to say, category theorists say a category C is complete, sometimes small complete, if every small diagram has a limit. Small diagram is a diagram whose shape is a small graph. And it's finitely complete if every finite diagram, that's a diagram whose shape is a finite graph, has a limit. So the theorem is the following are equivalent, TFAE. One, the category is complete. So then it has all the limits, all small limits for any diagram whose graph is a set has a limit, whose shape is a set has a limit. So in particular, it has products because those are special cases of small diagrams. So general products, the I-indexed ones. And it also has equalizers because those are also given by a special case of diagrams with, in this case, a finite diagram with only two vertices and two edges. That's enough. So if a category has products and equalizers, then amazingly, you can construct a limit for an arbitrary diagram. And we're going to begin next week by looking at the reason that's the case. I'm not going to do a detailed proof, but I'm going to give you the idea behind it. And there's a similar statement for finite limits. So again, the following are equivalent. So in this case, it's that the category C is finitely complete. So if it's finitely complete, well, we can't expect it to have arbitrary products, because if I is an infinite set, that's an infinite diagram, but it will certainly have finite products. So it's enough for it to have finite products and equalizers. But also if it's finitely complete, well, we'll have finite products, but in particular, it will have the empty product. That's a very simple finite product. So it will have a terminal object. Another equivalent statement is that C has a terminal object and pullbacks. And as an exercise that you can think about, which is quite a nice little exercise to get your mind around these things, irrespective of the notion of the general notion of limit and the notion of finite completeness, try to convince yourself that statement 2 and statement 3 here are equivalent. So that just concerns finite product equalizers, terminal object, and pullbacks. So exercise, prove 2 to 3. Yeah. Okay, so I'm very sorry for overrunning by 3 minutes. Anyway, that's everything for today. The notes will be online at some point. I've got a busy day today, so I'll try to put them up as soon as I can.